everyone, my name is Chantel, and for this Riviera-PRO video, I'll be going over the drivers and readers viewer and the Dataflow window. These two tools are very useful when it comes to tracing signals during debugging. By using them, you'll be able to get a better comprehensive understanding of how the many levels and objects of your design all flow together. So, in this video, I have the Verilog frequency meter example opened. You can find this in Riviera-PRO's examples folder under Verilog. First, go to Preferences under Tools in the main bar, go to General under Simulation, and then make sure Generate Data for Dataflow is checked in order to use Dataflow. Click on Apply and then OK. Now I can head over to the Example Designs macro file and execute the script. So with the simulation done, I'm going to switch over to the debug perspective and go to the simulation's waveform results. Now I'm going to demonstrate tracing a signal using the drivers and readers viewer, and I'll do this starting with LEDA from the test bench. Double-clicking it opens a new tab that shows where it was declared. While simulation is still running, when I hover over LEDA, the text turns purple and a small drop-down button appears. When I click on this, a context menu appears, and in this menu, you have the Add To option, as well as Set Stimuli, Breakpoints, Show the selected object's declaration source, and showing it in the Objects viewer. Now I'll add this signal to the Drivers and Readers window, and now you have information for LEDA. If you ever need to pull up Drivers and Readers, just click on this button here. Now, in this window are two lists. One is for the drivers that drive the added signal, and the other is for the list of readers that get their values from the added signal. In this drivers list, there's information for the name of the driver, its hierarchy path, the name of the driven object, and the hierarchy path of that driven object. The readers list contains only info for the reader's name and its hierarchy path. Now let's trace the path of how LEDA gets its value by clicking on the name of the driver. This opens up the location of the driver within the source code. It shows that LEDA got its value from this assign statement located in hex2 LED. We can then see that this LED object is being driven by the value of hex. So let's trace this back even further by adding hex to the drivers and readers window. With the window updated, it looks like the driven object's name is BCDU. And we can also see that the reader is the LED object at the assign statement on line 23, as we saw earlier. Clicking on the name of the driver again, we're led to an assign statement on line 89 of bin2BCD, where BCDU is being driven by BCDUI. Let's continue to trace by adding BCDUI to the drivers and readers window. Click on the driver's name, and we could see that this signal is driven by this always block. Scrolling down, we can see that aside from the value it has when reset is true, BCDUI gets its value from BCD. So let's add BCD to the drivers and readers window, and it looks like it's driven by the same always block as BCDUI. Scrolling further down the code, I can see that this is where the tracing path ends because BCD is a shift register. I'm going to confirm this by using Dataflow, but before I do, I want to mention that you can see your tracing history in the drivers and readers window by using this drop-down menu, and it'll be sorted from top to bottom, with top being the most recently added signal. You can use this to see how far you've traced back, or just use it to see what signals you've already traced. Now we'll go ahead and add BCD to Dataflow using the same context menu and clicking on Dataflow. Outside of this option, you can normally access Dataflow by clicking on this button. I'll switch over to Documents perspective to get a fuller view, and here we have our Dataflow window. Already, you can see BCD highlighted in red, and we can confirm that BCD is a shift register since the wire goes back into BCD. Now I'd like to give a brief overview of Dataflow. This is a tool that allows you to explore the connectivity of a simulated design and analyze data flow among various design elements, like instances and concurrent statements. It's kind of like the drivers and readers window, but here it gives a graphical representation of the connectivity. In Dataflow, you could change the display mode into hierarchical, flat, and gray. The default view you see now is hierarchical mode, which displays the structure of the design with the contents of each design unit being enclosed by a rectangle, which signifies its grouping in the hierarchy. In flat mode, all the items coming from all units on all hierarchy levels are flattened and displayed as a single level diagram. Instead of the rectangles acting as a boundary for the hierarchy region, the small vertical marks across signal lines indicate the region crossing. Lastly, there's gray mode. In this mode, all objects displayed are grayed out until you start tracing a net, which will then highlight the items that read or update the trace net. This helps to easily distinguish the items being traced and make them easy to recognize, which is helpful for large and complex data flow diagrams. The other ways that you can add more items into the data flow window are by dragging and dropping a hierarchy region from the hierarchy window, or by dragging and dropping signals from the objects window. When you hover over a graphical block or a signal, a small tooltip will appear giving info such as the name, object type, and source code language. When you right-click on a hierarchy region, a graphical block, or a signal, you'll open up a context menu that can let you discover, which is basically expanding the region, hide, which minimizes the region, focus, which opens up a new data flow window that isolates the view to only that selected object, expand net to both drivers and readers, or just to one of them, and many other options. You can also expand both drivers and readers of a signal by double-clicking on the signal. Expanding nets can help with tracing a signal graphically to see how the inputs and outputs are connected through the hierarchy regions. Going back to BCD UI, I'll go into gray mode, and if I just continue to expand to readers, I can confirm that the path of LEDA that was traced earlier using the drivers and readers window was correct. With that confirmed, I'd like to add the signals from instance U2 into the waveform view to see how the signals from U2 and from the test bench all interact. To do this, I just highlight the instance or object I want, right-click, then Add to Waveform. Now all the signals from U2 have been added. I'll reset the simulation, click on Run, and now I have the waveform results of the signals from both the test bench and U2. A very neat thing about the waveform viewer is that it cross-probes with the data flow window. This means that as I move the cursor around in the waveform viewer, the data flow window will also update in real time based on where my cursor is on the timeline. If I move my cursor to the time where bin input is 160, when I go back to the data flow window, I could see that bin input is also 160. If I reset simulation again, and run simulation until the specified time step, you could see the data flow view update in real time alongside the waveform view. And that concludes it for this video on the drivers and readers viewer and data flow. If you ever need to look at your design connectivity to see that your design is working as expected, these two tools are the way to go. And with cross-probing with the waveform viewer, tracing signals during your debugging process has never been easier. Thanks for watching.